All right, so our next unit is going to be all about work, power, and energy. And we're starting off with looking at this little diagram right here. This is one of my favorite PhET simulations. If you Google PhET, you can look at the energy skate park. And what we've got here is a frictionless environment. We've got a guy going up and down this little track, and we see this little pie chart. And this pie chart next to his head is representing his kinetic and potential energy. If you look at the top right corner, and I don't think I can do much besides put my pointer over here. If you look at this top corner right here, the right corner, we can see that the potential and the kinetic energy and the thermal energy are represented with green, blue, and red. And what we see is we see this pie chart. This pie chart represents the fact that the energy throughout the system is going to remain constant. This is our first conservation law for our units so far, this conservation of energy. We see at the very top it has more kinetic or more potential energy, and we see at the bottom it has more kinetic energy. Potential, kinetic, potential, kinetic. And really we're just seeing kind of like a transfer from one form of energy to the other and one form of energy to the other. And if I pause him, we can see that most of his energy at the top is potential. Most of his energy at the bottom is kinetic. And right now this should really be a review from last year. But let's turn the friction on the track. We'll give him just a little bit of friction. Now think about what's going to happen to the pie chart itself, but then also to the values over here. Are you ready to see what happens? Okay, so we see still mostly potential energy towards the top of the track, but now thermal energy is starting to play in here. And thermal energy is something we're going to talk about throughout this unit. At the very bottom, we see mostly kinetic energy with just a little bit of potential because he's above the ground right there. I think the track's in between him and the ground. And then the thermal energy is beginning to increase. Continue on. I see that that thermal energy value is beginning to increase. He's starting to go high or go less high, go at a slower speed, losing energy in the potential and the kinetic sense, gaining thermal energy. But the total energy for this system is remaining throughout the system. And this is really the law of conservation of energy right here. So let's go over to our Smartboard document and start taking some notes. All right, so this unit's going to be about work and power and energy and momentum and impulse. This is really the big idea for what is for us Unit 3. And if you've got the time, you might want to check your old physics notes. Find your old honors physics or regular physics notes and really look through these notes and look for the notes from last year, because this should be a review in some senses. We're just going to dig really deeper into these concepts, talking about work, energy, power, momentum, and impulse. And if you've got those notes from last year, you can do some quick references that might get you a little bit faster at remembering and recognizing concepts. So the first thing in this unit that I'd like to discuss is the law of conservation of energy. And if we think about the law of conservation of energy, really what we're talking about is that the total energy before something takes place is going to be equal to the total energy after something takes place. Some people say the total energy in a system cannot be created or destroyed, only transferred. Any of these answers will work. So we think about energy not created, not destroyed, only transferred. And some people might start to think about, well, what about when I produce energy or I generate energy? And all we're doing in those situations is converting it from one form of energy to another. We cannot produce energy. All we can do is convert it from one form to another. Now, the two big types of energy that we're going to talk about throughout the year, and let me pull up a new slide, is going to be potential and kinetic energy. Potential energy, obviously, is energy at rest, but we want to give it a more technical definition, a more accurate definition. We're going to say it's the stored energy due to an interaction. For example, when we're talking about gravitational potential energy, we're discussing the potential energy as a result of the interaction due to gravity. Now, the Potential energy symbol you may have remember from last year is going to be PE. Sometimes when we're talking about gravitational potential energy, it gets abbreviated as GPE. But we are up into the big leagues now, and our concepts now are going to represent potential energy with a capital U. A capital U. And because we're going to be talking mainly about gravitational potential energy, I'm going to give a small g right here to designate that I'm talking about the potential energy due to gravity. Just a reminder that the equation for potential energy is going to be mass times gravity times height. So we have to think about the mass of the object in kilograms, the gravitational pull on that object, which on Earth is 9.8 meters per second squared, and the height that that object is standing at, or is, I shouldn't say standing at, but that object is sitting at. The other type of motion that we're going to be discussing a lot is going to be kinetic energy. Kinetic energy. And kinetic energy is going to be energy due to motion. Kinetic energy. Now, kinetic energy is sometimes represented as KE, but we're going to just go with simply K, a capital K. And our kinetic energy is going to be equal to 1/2 multiplied by the mass multiplied by the velocity squared. Now, when we're thinking about this style of problem, we have to kind of keep one thing in mind, and the book talks about this concept just a little bit. We're going to be talking about translational motion. So for all these examples, we're using the idea of translational motion. When considering translational motion, the idea is just that the object is not spinning, nor is the object changing its shape or anything about its shape or internal energy while it's in motion. So it's not rotating and it's not changing its shape while it's in motion. So really we're considering the fact that the motion of the entire object isn't rotating, it's not changing its shape, we're not seeing a mass change, we're not seeing some of these variables that could influence the potential and kinetic energy. We're just seeing a straight up object moving, everything is going well, the object is not rotating, the object is not changing its shape. Next, let's do one example and then we're done with conservation of energy. So let's go back to our classic roller coaster examples from last year. So let's say that we have roller coaster with mass m and it's rolling down height x in the y. And I really want to know what is the velocity of the ball or the velocity of the roller coaster at the bottom of the hill. So this is where conservation of energy can come into play because at the top the object is going to be at rest, and when it's at rest it's going to have both potential and kinetic energy technically. So PE initial plus KE initial is going to be equal to the potential energy and the kinetic energy of the roller coaster at the bottom. So PE final plus KE final. Now, how many people are going, hey, I thought you said we were going to use capital U and capital K? I know I did midway through writing that. So let's write it out like how we want to. So U plus K is equal to, and that's both initial, are equal to U final plus K final. Now we're going to make two big assumptions. We're going to assume that at the top of the roller coaster it has no motion, that it has no motion, it's just preparing to go. So this is going to be equal to 0. So we are going to eventually just cross that variable out. And then let's say at the bottom that it's right at the ground level, so the potential energy at the bottom will be equal to 0. This leaves us with U initial plus 0 is equal to 0 plus K final. Simplify that out. U initial is equal to K final. Very interesting. Now we can simplify these equations even further. We said that our U is equal to mass times gravity times height, and that our K is equal to 1/2 mv squared. Well, there's a variable that can be canceled out here. Which variable is it? Do you know it? It's the mass. Good. So now we're left with the gravity multiplied by the height is equal to the mass multiplied by the velocity. And by the way, this is velocity final because it was kinetic energy final. I'm going to scroll down just a little bit. We want to solve for the velocity, so we need to get the v alone. So first thing we can do is we can multiply 1/2 over. So we have 2 multiplied by g times h is equal to v squared, and this is v final, of course. Take the square root of both sides, and now we've got our velocity final is equal to 2gh. Now I'm not going to put any numbers here because I don't need to right now. We don't want to focus too much on just calculations. Instead, we want to focus on the process of getting to this problem. And this is going to allow us, at the very beginning, we knew that the energy had to be conserved. Let's get a highlighter for fun. It's been a while since I've used a highlighter. But we knew that the energy had to be conserved. The energy before had to be equal to the energy after. Now, this is an idealized problem. There's no friction being that's going to contribute to energy being dissipated in a different way, which is ideal, but we still can get to where we want to be in terms of solving for the velocity final. All right, that's it for conservation of energy.